Do 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 do. Well, it looks like somebody's here, and I'm here. Let's see what our delay is like. I give a little wave. Let's see. Are you still streaming? It's unclear what my lag is like. That's alright. Well, we'll just carry on with it and we'll see who shows up. Oh, man, it's like 30 seconds of lag. That's alright. One thing I will need to do is make sure that this PCB stays in focus. For those I have streamed with before, one of my big problems is forgetting to switch back to the correct view. So we'll see if that works out, and if it doesn't, somebody can just yell at me and I'll fix it. So I think this is pretty well in focus. I've got a little monitor off camera that way. That'll help me cheat on that a little bit. Let's see if we. That's pretty good. Maybe we get a little bit closer. Yeah, that's kind of interesting. So I've already started a little bit of assembly before I thought I might just put it up on stream here. So I've done a few components already. I put in this IC, which is going to be the driver IC for my LED dimming. That is an AL8860 WT, which is a T-slot package. It's basically turns the LED into a little buck converter. And passes a regulated amount of current through the LED package itself. So that's that AL8860, which it's new to me. I've never tried it before. And in fact, when I got the parts in from DigiKey the other day, I tried doing a little fake up with some magnet wire, and I just could not, without a PCB, solder it to that fine of a pitch. I don't really have a breakout board that would fit it either. So I abandoned that. I ordered the PCBs in. I'm just trying that. Oh, Kenneth Finnegan's in the room. Kenneth Finnegan, I was hoping you'd show up. Well, that'll be delightful. Kenneth, I'm streaming on my other channel. Kenneth Finnegan has been KWF for so long, and I've been like 17 different identities. But that's just life. But Kenneth, you can be a moderator in this stream too, so that'll be fun for everybody. Okay, so I was saying things I've already started on. This AL8860 chip, there's an inductor here, which, let's see, what is the value of that inductor? That is, there we go. I want to say it's like 10 microhenries. It's a VLS 3015CX, of course. 470 microhenries? That seems awfully high. I don't think I entirely believe that that's true. Let me see here. I know this is stunning streaming right now, as I'm looking up things on the internet live on stream. Maybe you can watch my dancing tweezers as I look this up. That is 47 microhenries. That makes a lot more sense. Alrighty. Kenneth wielding the wrench of power. That's always a good sign. So, alright, so AL8860, inductor, Schottky diode here. I bought 20 volt rated ones, which is actually a little bit lower than I think I would like to use. But as I'll talk about a little bit later, I screwed up this PCB, so I have to order a new one anyway, so that's fine. I'd love this ultimately to be able to run off of up to like 24 volts, and I probably would need to pick a new regulator for this project anyway. But that's alright. So I'm going to go ahead and solder in R6 and R7 here. And then C1. So R6 and R7 will be these little boys. Those are 0.1 ohm 1% resistors. And these are set resistors for this product. These set the nominal maximum average current for the buck converter that this circuit creates. So we're just going to gently peel that back. And I get these components, just the basics of these components in place and finished. And then maybe we'll take a little peek at the schematic for this thing. And then pretty soon we'll see where I screwed up. Where I screwed up is not actually in the LED control part of this. Where I screwed up is in the PCB layout. So that will be just fantastic. Struggling with resistors on camera. So what I've done here for this PCB, and we'll look at the data sheet for that AL8860 in a moment. The formula for the average current through the buck converter is 0.1 over the resistance in between two of the pins, between the set and the ground pin of this IC. So if you have a 0.1 over 0.1 ohm, you have 1 amp of current. If you have over 0.2 ohms, you have half an amp current, and so on. So I have these two different pads, R6, let's see one here, R6 and R7. I'm going to put 0.1 ohm resistors on both of them in series, which means I'll have an average of a maximum current of half an amp. I'd ultimately like to try this out at 1 amp, which it is nominally capable of handling. I'm going to try it at half an amp first, and then I'm just going to bridge those pads in a second prototype and see if it'll do 1 amp. Ken says AL8860 is rated for 40 volts. Yeah, no, for sure. The Shocky diodes I purchased, these little guys, are only rated for 20 volts. So that's going to be the limiting factor for this evening. Let's see here. This is my first time streaming from the new workbench setup, which is very exciting. I don't have a great way of showing you my new streaming setup because I'm using it to stream. Yeah, the diodes are my limiting factor. A lot of here, as I solder, we can talk a little bit about what this is ultimately going to be. So I put up a post on my blog about this yesterday, which is at jeff.glass/blog. The gist to this project, and it's a long time coming, has been creating a little tiny DMX controlled moving light. And my previous version of that light was really tiny, but I didn't actually put the control circuitry or the dimming circuitry inside of the light. I just stuffed 2 servos and an LED in there, a high power LED, and then had this big giant external control rig to control it. That was, I mean, it turned out, it looked great if you didn't see the control circuitry. It was kind of chunky when you did. And so this is sort of part of my process of trying to miniaturize the circuitry enough that maybe it will fit in something like that form factor. I have that prototype light actually sitting out here somewhere. Maybe I'll grab that in a sec. So there's our 7 in place. R6. So this is all, the form factor for this is all based around an Arduino Pro Mini. So this inner set of headers is exactly the size of an Arduino Pro Mini, which I have one of somewhere sitting around here. The idea being that you solder some headers to the inner set of pads, and then you have the outer set of through holes to connect other things to, like you would with a shield. Here we go. Yeah, so for scale reference size. So there's a Pro Mini sitting on a breadboard there. Let's push this a little bit and get a better shot. Yeah, so you can see how that would with some female headers, slot right into the inner set right there, and then you can solder to these outer pads to do other Arduino-y things with. And then you have your LED dimming circuit. You have 2 ports for standard hobby servos, which are 5 volts signal ground. Spot for a big old 5 volt regulator to drive those servos. This will probably get miniaturized, but I got a little lazy as I was finishing. And then power input over here. And then in between the sets of holes for the Arduino headers is where the DMX reception circuitry goes. Which was I would say the central theme of my blog post is how that control circuitry goes. So we'll do R6 here. Alrighty. Maybe you can tell I didn't do a ton of prep for this stream. I was just starting to assemble this, and I thought it might be fun to put this online. And here we are, just me and Kenneth Finnegan and Bonus assembling a PCB. Alright, so that is most of the componentry here. The things I am missing are C1 here. Yes, and there's a component over here which I think is just a 10 microfarad cap that is meant to just be another, smoothing cap just next to that IC that's recommended in the data sheet there. Let me double check that before I get too far. Internet on stream. Internet on stream. Internet on stream. Yeah, that's a 10 microfarad cap, so we'll get to that in a second. And then C1, there's another 10 microfarad cap. Oh, that's easy enough. Well, let me grab terminal blocks, MOSFETs, connectors, headers, resistors. 0.1 microfarad, RS485 line drivers. Where are my 10 microfarad caps? There we go. 10 microfarad, 10 volts? Well, that's not going to be any good. What are these rated for? Yeah, this will be fine. 25 volts. Jeff needs a bottle of liquid flux. Yeah, it's true. It's true. So you are putting parts away as we go for a change, so I try not to lose anything. This is my 0.1 ohm resistors. Alright, so this is caps. 2 of those, which is board. Und we will solder the caps to the circuit board. Alright, so I'll try and be less bad at this one. I don't think I'm gonna do great, but I'm gonna be less bad. One thing I will say that I'm just being reminded of while Kenneth Finnegan is in the room and I'm soldering, I, for a long time, thought I was really bad at soldering. And then Kenneth pointed out to me that I was just using bad soldering irons. I'm not an expert, I'm not great, but that was easy enough. Oh, you couldn't see any of that. That looks pretty good. Look how good that looks. And there was one night we were at one or another of Kenneth's mad scientist apartments, and used, I don't remember if you have a Hacko or a Weller or something that was like a decent, $100 iron, and it made like an infinite amount of difference in how easy it was to solder. And within like a month, I went out and got I have a Hakko 888D, the new like digital version, and like it's not a fancy iron, but it's way better than a Radio Shack like $25, you know, miscellaneous, not regulated iron. All right, that's tacked in place. Kind of says, I have a Hakko 936. Yes. Maureen Lardy. Oh, my mother is here. Hi, Mom. She's joining us on a cool Tuesday evening for some soldering. Just like a normal Tuesday night, but like on the internet now, which is pretty cool. All right, so those are in theory the components for the LED dimming part of this circuit. So I wonder what order we want to do these things in. So this is the LED dimming part of the circuit. The Arduino goes on these sets of headers here. The DMX receive part of the circuitry will go in here, and then there's some connectors for some servos, regulator, power input. If I put the female headers in, it's going to be awfully hard to do this DMX circuitry later. So what I would like to do is just put the headers in and test this with an Arduino. But I think what I'm going to do is put the DMX components in now, even though I'm not really going to play with them tonight, so that I can use them later when I want to. Who else is here? Kenneth says, I bought the Hakko 9s, they were the digital replacement. Guess they look like... Yeah, I'm not a huge fan of the form factor. In fact, maybe I can show you. Upside down. Janky. This is the 888D upside down. Oh, I may be able to fix this. Hang on. Let me... rotate? Can I rotate you? Yeah, there we go. So this is the 888D. It's fine. Like, it heats up and it makes solder melt. The user interface on this is the dumbest thing in the world, right? It has two buttons, enter and up. If you press and hold enter, you get temperature select, right? You can select your hundreds digit, your tens, your ones. All right. If you press and hold the up button, maybe I disabled this feature. Oh, there we go. It goes into probe calibration mode. And now, if you make any adjustments to the temperature, which you can do easily, it's actually calibrating the temperature sensor inside the tip of the soldering iron to the temperature that you set. Like, you tell it, like, oh, I want to dial this into 750, and it says, oh, whatever temperature it is right now is my reading for 750. And there is no difference in indication between like which of these buttons, up or enter, which one should you hold to adjust the temperature. Unclear. In fact, I let somebody borrow this a couple weeks ago, and I put a sticker on it that says to adjust temp, hold enter, because it's a stupid piece of user design. In any case, let's go back to this. I'm going to spin you back around so I don't get too confused. Toys R Us branded soldering iron. Yeah, it's pretty cheesy. It's like blue plastic and awful. But it works. Like, it gets hot. Its temperature regulation is fine. It uses like Hakko tips, which are fine. It's for the amount of soldering that I'm doing day to day or week to week on it. Like, it's fine. I don't need a $500 soldering iron. But I definitely don't need I need better than a $25 soldering iron. So it's a good investment. And I bought this like 5 years ago, and I've never thought about replacing it or fixing it. We were going to do the DMX circuitry here. So let me pull out the components that I need to do that. Oh, pile of MOSFETs. All right, so we have RS45 driver. We have 10K resistors for biasing. We have caps. What am I missing? I am missing my switch. Slide switch. Yeah. that's all of the above. So let's get started here. I'm going to work from small to big. So I'm going to do the caps and resistors. Then I'm going to do the RS-45 driver chip, and then I'm going to do the SMD switch here. So let's put the switch aside. We'll put the caps and resistors here. We'll do the IC there. The DMX control part of this is like 7 components. It's actually exactly the same as this little guy, which is like the bare DMX Arduino shield that I was featuring in my blog post. Unsnap this here. So this is exactly what we're going to put together right now. So it's 2 sets of female headers, an RS-45 driver chip, a slide switch, some pads that you can hang a connector off of when you're done. So, and like I say, this is not the point of my experimentation tonight. I really want to get into this, but I think if I ever want to play with DMX on this, and I'm going to want to, I should put all this in now. So, let's pop this guy open. That's one. Actually, let's do. These are all on the 5-volt side, so I can use actually a 10 microfarad and a 0.1 microfarad cap in parallel of each other, which is either best practice or the worst idea in the world, depending on who on the internet you believe. So we'll get those soldered in place. Let's see. What did I do with? Here we go. I shoved a lot of things out of the way hurriedly to do that soldering iron peekaboo. Alright, so. Three. 2. Alright, let's tack these in. So, I guess continuing on a theme of talking about things while soldering. So the DMX receive hardware on, what I'm ostensibly calling an Arduino Pro Mini DMX shield is really, on the hardware side, it's really, really simple. So DMX is, for those who aren't lighting people, a 250 kilobit per second serial protocol, and the standard defines that it runs over an RS-45 compatible serial bus. DMX at its core is unidirectional, although there are some expanded and compatible standards that allow for bidirectional communication. It is the standard way of controlling contemporary lighting hardware. So whether that's like an industrial 20 amp dimmer that we're using to light up and dim lights, whether that's a moving light that has and more intelligent features like pan and tilt and zoom and color and gobos, like patterns that put into it. Every light speaks DMX, and the standard, which is put up by an organization called the ESTA, also specifies standard connector types, which is a 5-pin XLR connector. And interestingly, the primary communication conduit of DMX uses only the first 3 pins for ground, signal minus, and signal plus. And the other 2 sets of pins, depending on, were either you could use for a secondary DMX link, so another signal plus and minus, or you could use for, reserved for future use, like you use manufacturer-specific stuff. And so, of course, manufacturers seeing this, saying, oh, I really only need to use the first 3 pins, immediately started putting 3-pin XLR connectors on equipment, to the point that you sometimes see, like, fixtures that have both, like, professional theater uses and, like, DJ and band, flash and trash kind of uses, have both, that have a 3-pin set of connectors and a 5-pin set of connectors, so that they're sort of as widely compatible as possible. which is just the worst of both worlds. And now there is a de facto standard for squishing DMX connections into an RJ45 connector, which is permissible by the standard, but it's only supposed to be for permanently installed equipment. But if you buy like a cheapy LED decoder, that takes DMX in and like dims your LED tape and your creative animals from Madagascar, for example, that will have often just a cheapy RJ45 connector on it instead of an XLR connector, which is fine because they're cheap, like 20 or 30 bucks for 24 channels of dimming, cheap, but it's not really up to code. So in any case, all the hardware that you really have to add to an Arduino to be able to communicate with it via DMX or let it communicate is one of these little RS-485 transceiver chips. So this is a MAX 485, which is a Maxim part. It's an industry standard. The other one you see is the TI part, which is the SN75176. And you see basically one of those two chips in every professional or cheapy grade DMX product. And all that's doing is taking the serial data coming in from the Arduino and converting it into this signal that is compatible with the RS-485 standard. So it's balanced. It has a certain range of voltages that are permissible. Max makes a line of chips that are slew rate limited, just to sort of minimize crosstalk. This is not one of them. This is one of them, but I'm not really relying on its slew rate limiting for any practical reasons. Let's see. So this will be our passives. A couple of sort of just bypass caps right near the IC, and a couple of resistors that bias the signal lines to ground. Like there are 10K resistors to ground from both the signal lines. So that's easy. And then we'll put in one of. Oh, here we go. Come back here. So you stay there, and I come down here. Put in one of these. Ooh, which is my last one in the tube. This is a Max 485. That's that transceiver chip. So I guess I could put in my my other buys. I'm going to put in two more passives. So the Max 485 has two control pins on it, and if you enable one, if you pull one high, the chip is in transmit mode. If you pull the other one high, it's in receive mode. And while I also do this in software, I'm also going to put 10K resistors to ground on both of those lines, just so they default to putting pull down resistors on them, just for safety. We'll do that real quick. One thing that's interesting about DMX, so it's the standard covers the physical layer. What was kind of say? DMX receiver is just a 485 transceiver, which is RC45. Would you go with? Oh, Max 45. Yeah, exactly. What was I saying? Oh, so the interesting thing about DMX is the original standard was written in 1989 and was sort of ratified as a standard in 91. And it is still very much actively the standard for lighting controllers. There is not a newer physical protocol, a serial protocol that is used. That is the one. But of course, in the last 30 years, the amount of parameters that a given light may have has expanded wildly. So back in the day, it would probably have been, pan, maybe pan and tilt once we're talking like mid-90s when the first moving lights came around, but really just dimming. And nowadays, some of the fixtures we have in the rig for our current show are 40 or 50 parameters. There are media servers, right? If you go to a concert and you see a big video wall or projection sequence, those are being fed by a piece of hardware and software called a media server, which is just meant to spit video as quickly as possible to multiple inputs at high resolution. A lot of those, for simplicity's sake, respond to DMX as well, and those can have hundreds and hundreds and hundreds of parameters. One parameter, one byte might specify the X position of this piece of content, then another byte for this position of this piece of content. then playback speed and opacity, and all the other parameters you can think of for a video image. And they might be doing that while compositing 10 or 20 images at once in real time, because some of those images might be live feeds. So you start to have these devices with hundreds and hundreds and hundreds of parameters, and DMX as a signal, DMX as a spec specifies that it'll be an RS-45 bus. The communication will be 500 up to 512 1-byte values, and that's all over a single hardware line. And those values get spit out, at 250 kilobits per second, and then it repeats. So your maximum refresh rate, if you're sending all of those bytes, is something like 44 full frames per second, which is a perfectly fine refresh rate and a perfectly fine amount of data if you're just talking about some dimmers. But if you're talking about hundreds of parameters or hundreds of lights, it's not really practical anymore. So, as we pause to read Kenneth's question, max 45. So nowadays the distribution is not so much straight from lighting controller to device. In a simple situation, you might have a XLR5 connector on the back of your console, an XLR5 connector on the back of your first unit, another XLR connector on the back of the first unit, and you jump from one to the next, to the next, to the next, and so on. But when you're talking about more than, say, a dozen units, or lots and lots of units, that becomes pretty impractical. And the way we would say that in the lighting world is one physical bus, one line, one set of cables that carries 512 up to 512 bytes. That's one universe of DMX. So you might say, this light is plugged into universe 1, and I've given it an address of 10. I've told it that on this bus, listen to the 10th byte that comes in. And there's some preamble bytes. There's a break that tells it when the chain is starting. But listen to the 10th value that comes in. Or if it's a moving light, the 10th value that comes in is going to be your pan. The 11th value is going to be your tilt. The 12th value is the value that your cyan flag should be set to. Your magenta flag should be set to. Your iris, your zoom, and so on and so forth for however many values that light has. So the modern way of distributing DMX is to, rather than taking a bunch of cables and home running them to the lighting controller, we pipe all that data over a network. And there are a couple of different competing network protocols that are used to distribute that DMX data. Those two are called ACN, Architecture for Control Networks, or Streaming ACN, which is sort of a pared down version of that, or ArtNet. SACN is the one that's recognized and is an ESTA standard. ArtNet is kind of this indie thing that's been widely adopted. They both have strengths and weaknesses. They both have sort of varying levels of adoption. A lot of products support both nowadays. But what you would do is you tell your lighting controller to you hook it up to your lighting network. You hook it up to a switch, and then you plop these devices near your fixtures. We call them DMX nodes. It's basically a little mini computer in a ruggedized tourable box that plugs into your lighting network and has 2 or 4 or 6 or 8 XLR5 connectors on it, and you can configure what universe of DMX they're responding to. So you might say, hey, this node, you're going to listen to what I'm calling universe 6 in my control console, and you're going to put out those 512 bytes on your first port. You're going to this next port will be universe 7, spit out the 512 bytes corresponding to universe 7 on this port, and so on and so forth. And then in your lighting control, you would say, hey, this light is plugged into the port that I've told to respond to universe 6. I'm going to tell it that the address of that light is going to be universe 6 address 10, say, or 6/10. And then your lighting controller knows what network port to send that to, what address on the network to send it to. It pipes this data over ACN or ArtNet or other proprietary protocols to that node, and it turns it back into hard DMX data, and then it comes out and it goes into the lights. So that's like way too much information on how modern DMX control flows. But that's all right. We're almost done soldering this here. And then we'll be able to go back to experimenting. how is the audio out there in Streamsville? I've got a little cheapy shotgun mic sort of sitting about 3 feet away from me. I hope it's not awful. Not as awful as this soldering job. Let's see here. That's one side done. That's the other side. These little SMD switches are super adorable, and they're cheap. They're like 60 cents a piece. I love them. It's a double pull, double throw switch that you can just slot onto your PCB. So that's the DMX part complete. I'm going to put headers on this now, and I'm going to figure out the best way to test this LED dimming circuit. I'm going to put headers on this now. Let's look at the schematic real quick, and then we'll test it before we blow it up. Ken says audio is pretty good, just slightly overdriven. Oh, I can deal with that. Let's see. Let's just turn the gain down on that just a little bit. I also think, oh, you know what I have? Let's see if that helps at all. Let's see if that helps at all. The little mic I'm using has a plus 10 dB internal amp on it. I just turned off. Hopefully that still sounds good, or a little bit better, and it's still audible. Alright, so let's find our Arduino Pro Mini size headers. As I was ordering these PCBs, I saw the announcement about the Arduino Nano Every, which is their new IoT themed Arduino product, which is kind of interesting. They've got like a SIM card version, they've got a BLE version, they've got a Wi-Fi version, which I'm kind of excited about. I think that could be interesting. There's been a lot of Arduino on the internet products recently, and I've not been super impressed. I bought some of the particle hardware and was not super in love with that or its ecosystem. I found it really buggy, so I've kind of given up on that. Oh, I'm out of Arduino headers. Well, that's alright. We can find a way to deal with that. I have other headers. Worse? Sounds like you're talking into a bucket. Well, that's no good. Let's be overdriven and not in a bucket. Well, nerds, no headers. What are we gonna do about? Oh, maybe I have some more. I wish I had a camera so I could show you all the puttering I'm doing in this new desk setup. We'll have to do that at some point. Because I could just solder an Arduino in directly, but I have this pretty good feeling I'm gonna fry something. So I probably will end up just soldering some jumper wires to the couple of control points on its LED dimming circuit, and then ordering more headers, and this can still be a test prototype for other things. So why don't we, before we do that, let me roll over here and change view to the schematic here. Let's see if I can make that happen. That should do it. Pull it up so I can look at it too. Alrighty, so this is essentially the schematic for the board that we're assembling tonight. So easiest part, the inner set of headers here corresponds exactly to an Arduino Pro Mini. Let's see. Just watching my YouTube preview in the background, you are seeing the schematic. That's good. There are 2 sets of 3-pin headers here for the pan and tilt servos for the moving light that'll come along later. This is the DMX transmit and receive portion that we just assembled, right? So this comes from pin 0, digital 0 and digital 1 on the Arduino, goes via the switch to the input and output lines on the Max 45. I know it says 41, I just reused this symbol. The D2 and D4 are my chosen lines to enable transmit and enable receive, and those are pulled to ground by those resistors we added at the last minute. And then the plus and minus outputs, or out A and out B, are the balanced signal that comes out of this. Those are also biased to ground, and those go to this 6-position header here that I can also show you on a circuit board. So that is these little guys down here. Because so for a typical DMX device, you'd have an XLR5 male connector for input, and XLR5 female connector for output. Technically, for an RS-45 bus, you don't want a star or hub sort of layout. You want sort of a linear bus, mostly for like signal reflection issues, and to make it easier to terminate the line with the appropriate impedance at the very far end. So mostly, if this was installed in a proper device, you'd have an XLR5 male connector right next to it, an XLR5 female connector right next to it, and then you would either directly wire them together and branch off of one of those and put it onto your PCB, or you direct wire into one with some short wires and direct wire out with some short wires. I just put two sets of 3 pads here just for convenience, because that makes it really easy to wire in test connectors. And it also means if you mess up soldering your first one, you can cut the wires off and you have 3 more pads to solder to. Sorry, but let's go back to the schematic. Let's see here. Make that a little bit bigger. That's pretty good. Set that up. Yeah. So, schematic-wise, so we looked at the DMX section. This is all just like power conditioning. There's some caps. There's a 5-volt regulator that I'll put in at some point. There's this power input here. Let's go down to the A8860 buck converter IC. So this chip will run up to 40 volts, and it will basically put your LEDs, which in this place are represented by this 2-position pin header symbol, because I'm just only 2 bare pads that I can solder the LED tails directly to. Basically, those are put in line with an inductor, and then this whole circuit forms a buck converter, and the average amperage flowing through these LEDs is determined by 2 things. One, these 2 series resistors here, or this total resistance, as we talked about earlier, and if you put a PWM signal on pin 3 here, that will also modulate the amount of current that will be on average coming out of your output. At least that's the theory. And then this Schottky diode here is for when the field of this buck converter collapses. That provides your return path when the field goes the other way or something. I'm not an expert on buck converters, but this is literally what the data sheet says you should do. In fact, let's see. We can pull that up. Internet on the internet. Let me pull that up and show it to you. 1 second here. This is for Chrome. Let's see if this is... Ooh, it's gotten very grumpy on me. Oh, no. Oh, no, it's gotten so grumpy. Oh, it's gotten very grumpy indeed. Ooh, it's no good. It's actually lost Eagle now as well. Oh, I've done it so badly. Well, it was nice while it lasted. Oh You can just see all my Eagle tabs. This is some pro level streaming right here. Let's just go back to the schematic. We'll look at the data sheet. Never. So basically, the circuit is just mashing together. This PCB is mashing together these two ideas, right? This DMX transceiver chip and this buck converter idea, which I'm gonna hopefully test out this evening. Close up a couple things. The AL8860 be happier if you had a reconstruction filter, not to have the control line full on or full off. It actually makes it more meant for analog control. It does later in the data sheet, and I believe it talks about using that line specifically for PWM. Control pin says will accept either a DC signal or PWM signal. So I'm sort of trusting the data sheet. It does have a spec for down on page 5 for PW and DIM output current versus duty cycle at up to 1 kilohertz, and it seems to be linear with any frequency. So I'm sort of willing to trust it, but that's, I guess, part of what we're gonna find out when we test this thing. Doesn't behave with people. Put a low pass filter on it. Yeah, that's possible. Like I could just roll off some of that actual hard PWM. All right, well, let's go back to our circuit and figure out how we're gonna approach this. So, the PWM signal that I have chosen to use coming out of Arduino pin D3. So I could just bodge a little wire onto D3 here and use an Arduino maybe that's already conveniently on a breadboard. Wouldn't that be nice? Let's see. There we go. And in fact, I think that's what I'm going to do. But I'm also going to need an LED to hook up to this, and conveniently, I have one. So this is a little unit. Get it better right there. This is a little unit from LED Supply. In fact, it's just that little white PCB in there. Here, before if I'm going to start monkeying around with this, let me adjust my camera here. Go back to the autofocus on this camera is not great, but for stuff like waving this right up in the camera, I think it'll help. Yeah, there we go. So that little chip down there is 3 high power LED diodes. This is actually one of the remaindered ones from LEDsupply.com. It was like $6. You can run up to an amp through it, and at that point it outputs something like 300 or 400 lumens, which is pretty good for a little tiny chip. This on top is a little snap-in lens. They call this the 3-up style of their LED products. The LEDs themselves are a Cree LED at like 4K to color temperature. Not great CRI, but like again, this is an experiment, and they were remaindered, so I'm not super sad about it. So I am going to start with those LED wires. So this will be my load. I have tested this up to 750 milliamps, not for very long, but I have. So I feel pretty good about putting half an amp through it to start. So I'm going to solder those directly onto the LED jumper pads here. Focus, there we go. Those will be where that power wants to flow through. Embarrassingly, I didn't label which was the anode and cathode of those LEDs, so I'm just going to take a little quick peekaroo at the digital schematic off camera here and see how that is meant to be wired. So the inductor is wired to the downstream side, so that should be fine. So I will do this. Let's see. Higher than PWM is recommended. Lower than 500 Hz PWM frequency. Higher dimming frequency can be used at reduce of dynamic range. Yeah, dimming frequency on an Arduino is probably 1 kilohertz. I don't know if someone wants to Google it. I could also badge like a 10 nanofarad cap across these across the input pads. And I'm going to be doing this all off board anyway. So that's easy enough. Alrighty. Let's just do a little sock there. Alright. So that's my load. It's classy. Let's see here. Now we're gonna need some control, and we're gonna need some power. So for control, I'm just gonna run a couple of bits of wire over here. Just do so. This is a spool of just bell wire that I bought at either Halted or Excess Solutions in Silicon Valley, and threw in my suitcase and brought back. And I've used up one big spool of bell wire in all my years of doodling around. And this is a second, like, one that's 3 times as big, and I expect it to last essentially forever in all of my projects. So let's put in this will be our shared ground. And this will be our PWM line. That I'm going to hardwire to D3 here. And the nice thing about having this external set of pads is that if I ever, order more Arduino headers and can, actually put an Arduino in here, this would be a really easy thing to work around because I have 2 sets of holes to go through. All right, so those are a little long, I suppose. Trim those up. We will bring this bad boy in the picture. Let me actually get a little bit more of a bird's eye. That's pretty good. Serve. Alright, so I was messing around with this LED screen earlier, but that can all get unwired. And this will go to ground, which is this guy, and this will go to D3. This is this guy. Okay, so that will be my test setup for now. I will basically set that to run just a ramp up and a ramp down of PWM maybe is a good thing to test with. That seems reasonable. Man, realizing if I have my little laptop that I'm streaming from has 3 USB ports, which are being used by the microphone input, the camera input, and the mouse. So I guess I'm just not going to use a mouse when I'm programming this. When I get this plugged in, I will take us over to the Arduino IDE, and you can watch me write some really stunning PWM ramp code, I'm sure. Ken says, I think the first spool of bell wire was my birthday present or graduation present or something. Yeah, I definitely have inherited some wire from Kenneth over the years, in addition to other goodies and shenanigans that have come my way. I have this little, this spool of, like, number 24 brown flexible wire that I definitely bought at Excess Solutions last time I was there. It's, yeah, lots of fun presents from Silicon Valley for sure. Alrighty. So the OBS threw up all over me when I tried to get it to show Chrome So I am going to hopefully get it to show the Arduino IDE. Give me 1 second here. There we go. Oh, that worked pretty well. Alrighty. Get things a little rearranged, and we will just do a little cheapy Arduino code. Let's set up a name for this. And then we'll write a little ramp code for I equals starting at 0, I is less than 256, increment. Right, LED pin I. We're going to define our time step, constant delay time equals 10 milliseconds per step, which means it'll ramp up over 2 seconds. Let's do 5 milliseconds per step. Delay time. We'll have it delay times 50. Oh, boom. Thank you, Kenneth. You're looking at the breadboard. Beans. All right. You should be looking at the code now. Thank you, Kenneth. Kenneth, I don't know if you were in the room yet when I said I was definitely going to forget to switch the view at some point. And here we are. So, like, I'm glad I can fulfill that promise. Is equal to 0 plus. All right, so we're gonna save this. We're gonna call this AL8860 PWM test. Sure. Code, yeah, love code. Look how exciting code is. Code. Let's see. Does code is code readable in this scale and format over the internet? Like, is this at all worth showing? Do you like increase the size? I mean, this is like the world's least interesting code, but here we are. Let's do big code. All right, we have the Arduino Pro Mini hooked up. It is 5 volts, 60 megahertz, COM7. Upload. Oh, that's not going to go well. Yes. Oh, int I equals 0. Good code, good code. Debugging code on the internet. Forgetting semicolons on the internet. Alright, uploading. Very exciting. It uploaded! Yay! Yay! Cool. So, now it's time to put some power into this thing and see what happens. Yeah, that's gonna be an exciting time. Maybe we'll put a couple of bus wires on that power input and I'll feed it from my current limiting power supply, so hopefully it doesn't actually blow up in my face. So let's remember to take you back to real life. There we go. Alright, so that should be doing a PWM ramp now. Back over here? Yeah, cool. And I will put a couple more of this bits of bell wire just onto my power input pads. The sort of like end goal for me of all of this is, you know, to make this moving light product that would, moving light toy that would have some kind of external connectors on it. So these pads are literally just like, you know, 0.1 inch spaced through hole pads to solder some wire onto, with the idea that at some point I would, pick an external power connector, or like think about the form factor and have, honestly, for like how small I dream of this thing being, maybe just some expose these pads through a hole in the case, and maybe you just are meant to solder directly to them with your external connector. I don't know. This is not enjoying being soldered to. That's fine. Okay, I'm gonna get rid of some of this schmatza just to give ourselves a little more room. So there's a non-zero chance that I've done something wrong and something does blow up. So let's think about safety first. Get out some of our handy dandy safety goggles. All right, let's see. Are we still? Yeah, we're still going over here. All right, I'm just gonna get the ye olde safety goggles on, and hook up a little bit of power. So these are gonna be my power input lines. Pull comments back up here. Kind of says, been writing too much Python. Yeah. I imagine Kenneth's running his own little pocket internet over there. I'm sure that's been a not code-free experience. So this is the lines coming from my variable power supply, which is an old Elenco precision power supply that I got at a hand pest for $15. 30 volts, half an amp. It does me fine. All right, how am I not going to blow myself up on this? So if you leave the PWM pin floating, it should pass the maximum amount of power specified by those two resistors. If you ground it, it should output no power, and if you PWM it, obviously you will have an amount of power in between. So maybe what I will do, just for safety, is start by just grounding that pin. All the ground pins on this PCB are linked together. All the ground ties are. The ground plane is basically complete on the other side of this PCB. In fact, you can see on this other one here. There's one big ground. There's a lot of, a big old ground pour, and there's like one little trace that I couldn't figure out how to route that jumps across things. So in theory, when I give this power, it should not turn on at all. This LED is significantly bright, so I'm going to sort of push it a little off angle from the camera. But if it turns on, I believe you will be able to see it even on camera. So I'm going to turn the current limiting on my power supply all the way down and apply some power. So I'm not drawing any current at all at the moment, which is quite good. So if I plug that in, I will attach this back to ground. I'll attach this back to ground to D3. Good. Now this could all be incredibly anticlimactic, and then it may become a stream about troubleshooting on camera, or it might be just a stream about Jeff not streaming anymore on camera. But here we go, and maybe we'll do a little troubleshooting. That might be kind of fun. I wish what I need is a camera that shows like the full bench. We could show you what the scope is doing without like plopping it right here in front of me. But we'll see if we get to that point. Maybe that'll be a good point to stop for the evening, and we'll pick it up on another day. So I'm going to turn the power supply back on. You know what? Here's what I'll do. If the LED doesn't turn on with this driver, that will be sad for this experiment, but I will at least plug directly into the leads here and try and turn this LED on and try and give you a sense of how bright it actually is. And we can call that a successful end no matter what happens. Ken says, "Boom." I have a good feeling about this. I think more likely nothing's going to happen. There will be some error and just it will do nothing. All right, turning up the power, turning up the voltage. Oh, oh! Can you see that? It turned on. Oh, that's cool. All right, well that was at about 6 volts. Ooh, let's turn the power back off. Let's see what the minimum voltage is. I think it's 5 volts on the AL8860. Let's see if that's true. AL8860. Wow, I wasn't expecting it to do anything. That's kind of exciting. Wide input voltage range 4.5 to 40 volts. The forward voltage on the diode stack itself is, it's 3 white diodes in a row. It's probably about 10 volts. Well, that's exciting. Okay, cool. All right, let's try that again. Let me pull up more things. All right, here. So, all right. So there's that. Maybe, no, we'll just go for it. So, turning on the voltage again. 2 volts, 4 volts, 6 volts. It's certainly ramping. Look at that. So that's at about 7.5. Oh, I'm also current limiting as that increases. Let me increase my current limit. Can you see that ramping there? Yeah, I think you can here. Let me turn off a little bit of the overhead lighting on this bench. Well, that's very cool. Excellent. I'm going to take a 30-second break, and I'll be back with you in a sec. All right, we're back. You can hear me. You can wave under here.
I'll wave under here?
Yeah.
Hi!
My wife is here. That's exciting. Hello, Internet. This is new. This started happening right just before you walked in. Maybe you knew you were coming. It's the beating of my heart for you.
Yeah, let's say.
Yeah, how cool is that? I'm gonna see if it gets brighter.
It looks like it can. Have fun, everyone.
Yeah.
Bye.
Thanks, hon. All right, so I'm really curious. So the whole point of this driver is that it is, doing efficient current limiting on these LEDs. Ken says audio. Hi, Mary. I did say I was taking a short break there, Kenneth. I did that by disabling the audio. And by disabling, I mean unplugging. So if I turn the voltage up, oh, it's quite a bit brighter. Yes, bright as the glowing sun. So this is now, I'm at 10 volts on the input power. So that's probably, just over the forward voltage of these 3 diodes in series with each other. Just interesting. So in theory, right, this is all, doing current averaging on this buck power supply. It shouldn't really matter once I'm over the forward voltage of the diodes what input voltage I give it. So if I crank this up to 20 volts, no appreciable difference in brightness, I would say. I'm sure it's hard to see on camera, but there's locally no appreciable difference between 10 volts and 20 volts and 30 volts, although the noticeable difference on my bench is that, of course, I'm drawing less current from my power supply. That doesn't make a lot of sense. Or does it? Interesting. Well, that's very encouraging. It probably means I have to fix some Arduino code because I broke something. But that's okay. It's very exciting. Let's go back to Arduinosville. Figure out where I messed up. RG5 analog right LED pin I delay for I equals 255 to 0 I minus minus. That would do it. Alrighty, so let's go back to the real world. And we will turn on our supply voltage again to our usual 15 volts, and we'll have it ramp up and down. Well, that's pretty nifty. I'm not going to say surprised, but I am delighted that this works. So this maximum brightness is about half an amp, and nominally, with proper heat sinking, you can pull an amp through this chip. I don't know how to give you a relative reference for how bright this thing actually is, but I would say it's, in my world, this is like 15 watt BR30 bright. Like not a not inconsiderable amount of light, and this lens shrinks it down to about like 17 degrees, which is pretty great. Wow, that's delightful. So part of the, I'll turn this off for a sec, give it some more light on the table. So part of what's delightful about this, so when I was thinking about how we were going to dim LEDs on this system, I was thinking the way that like most of our cheapy LED dimming products work is with a big MOSFET that had, not big, but like, a reasonable chunky size, just to dissipate the heat that it loses passing through the MOSFET. The entire componentry of this, which is cool to the touch, oops, here we go, is all in this little TSOT 25 chip right there, and an inductor and a cap and that IC. It's a very miniaturized unit, and I in theory can create an amp of LED dimming through that. That's awesome, right? That opens so many doors, as opposed to to give you a scale reference, and this is for a single amp probably overkill. But so I have the LED tape is actually lighting this table at the moment. I have this dream project to put that into a dimmed system that I would build, and I'm thinking about using some of these, which are, what are these, IRLB 8721s. I think that's a pretty standard package, and I would probably dim 5 amps through that, and not worry about it too much, but there would be some heat management to do, and especially if I'm putting 12 of these into an enclosed surface, I would be a little worried about heat buildup. But this is cool to the touch, up to an amp, little tiny package. That's super cool. Wow. I'm going to call that a success. I'm going to turn this back on and just enjoy the fact that it works, and it worked first try, which is super cool. Dare we go higher? I think not tonight. I think we're not going higher tonight. I think this is going to be where we end it. So thank you for joining me this evening as we mess around with dimmed circuitry. I think next steps will be bridging across one of the resistors on this board, which would take us up to an amp max, which would be super exciting. It'll be getting an actual Arduino on here and doing this dimming via DMX. And then starting to think about how this fits inside of a moving light enclosure. Oh, I did promise I would show the mini moving light, because I realized that I had not touched this project in a long time. So, make sure you can see that. Yeah, so this is the this is the form factor of the mini moving light itself. You can sort of see in relation to my hand for scale. It's a little tiny. It's literally just exactly the size of that servo, that LED PCB, and then there's a servo in this base as well. But this is all the control circuitry. So that's a Arduino Pro Mini. That's a little buck converter circuit. This is what are you? An ULN 2003, which is basically a bunch of 2222 transistors in a DIP package. This like Baji wiring here. There's a 5-volt regulator here. There's a couple of control buttons for testing. So like the whole thing, you know, you could compactify this, but as built, it's not really a tiny moving light. It's a tiny moving light with a big fat butt. But all of this, you know, power-wise, control, dimming, is represented here in this circuit board. So I'm really stoked. I think this is great. I did also promise I would show you what I messed up about this PCB. I didn't run a full design rules check one last time before I sent this to Fab, and the pads for the pan and tilt servos touch right here. So for testing, I might file those down, but I do need to order another version and space this out by like another 0.5 inches, which you know, is not the biggest change, but an important one. Kat says, super cool to touch, just like me. Yeah, I'm gonna call it a night here, y'all. We'll see you next time. Thanks for tuning in on a casual Tuesday night in Jeff Glassland. Y'all have a good one.